Alright, well, today I'm going to be talking about how we know we are close to solving an NP-hard problem. See, last night I was watching this ad for a cloud computing service, some website, and they used the example of the Traveling Salesman Problem. Now, this is a classic introduction to NP-hard problems. The idea is you have a bunch of different cities, represented by dots here, and you are a traveling salesman who has to visit each city, so you pretty much play connect the dots to make a route. However, your goal is to minimize the distance, because as a traveling salesman, every amount you have to travel, takes money, it takes time, costs supplies. So you try to get to these cities and complete your route as fast as you can, which means the shortest distance. So how do you minimize the distance? Who's to say it's not better to, do something like this, where you go out a little bit and then get that one, right? That's why it's an NP-hard problem, because you have to check, does every single, out of all the different connections, what is the possible, which ones are the best? And so it sort of makes it really, really difficult to compute, because you're doing an O of n squared calculation, right? For every city, you have to check the path to every other city and see if it's most efficient, and then build an overall route from it. So how do we know our algorithms are anywhere close? Because let's say we have iterations on the bottoms, like our versions, and then distance on top. Right? So V1, let's say we're up here, but then V2, maybe we made a very slight improvement, but the optimal solution is down there. How would we know? Right? It could be the same thing, but we're incredibly close, or we could be incredibly far away, or maybe our improvement, which looked really small, maybe got us incredibly closer to the optimal solution, which is down here. Now, of course, the problem is it's an NP-hard problem, right? The whole point is that this problem, we don't know where this line is. We're not sure where the optimal solution is, because if we knew the optimal solution, well, we wouldn't be trying to find it. So, how do we know where we are in relation to the optimal solution? How do we know we're even getting close for NP-hard problems? Well, we use something called a lower bound. See, we may not know the optimal solution for the traveling salesman problem, or any NP-hard problem, but we can calculate roughly what it would be, mathematically speaking. We know it has to be greater than some amount. So I'm going to demonstrate for you. For example, in the traveling salesman problem, there must always be n minus 1 edges, where n is the number of cities. So if we have a simple square, right, and we have the set of all possible connections, so these are all the different connections we can take, we know if we have 4 cities, n minus 1 is going to equal 3 edges. And so you'd see, to make a complete route, we only need 1, 2, 3 edges. And this goes for any route we make. So let's say we want to do this one instead. We can visit every city with n minus 1 edges, where n is the number of cities. So that's important to keep in mind, because now we know that we have a minimum number of edges. We know we have to have n minus 1 edges to visit every single city. But, of course, you might say, well, which edges, right? The whole point of the problem is you don't know which edge we're going to use, but we do know every possible edge. I drew it before for you, right? This is the set. These are all the possible edges for 4 cities. So we know the set of possible edges, And we have to pick a subset of that to be our solution. So let's say we do something like that, right? It's just picking edges from our set of total possible edges. So to create a lower bound, we know it's the minimum of this problem, the absolute lowest it can be. So if we simplify it even further, I can give you a really great example. We'll draw it all the way down here. So with 3 cities, we know n-1 is 2, so we have to pick 2 edges to make our root. In this example, it's pretty obvious that either that or that are going to be the most optimal solution. Because let's say my drawing skills are amazing and it's a perfectly isosceles triangle. We know we have to pick n-1 edges, and these are the total set of edges. So we know that the optimal solution should have the smallest possible edge in our set. So we look at it and we say, well, that's the smallest possible edge. So we know the optimal solution includes that one. And we know we need 2 edges, right? n-1. So we have to pick another edge. And regardless of where it is, like let's say we do have a definite shortest path where we have something, I don't know, like so, to keep it consistent. So obviously the hypotenuse would be longer. So it'd be better to go over and then down. So from our set of total edges, we've already picked this one. So we say, all right, we know that was the smallest possible edge, but we need one more edge. So we pick the next smallest possible edge. So we're going to pick the one over here, going straight down. And so that's our minimum. We know for a fact that there are going to be n-1 edges, and we know an optimal solution would only pick the shortest edges. Now, you might wonder, why is it not, why don't we just solve the problem like that? Well, let's have a couple more points sort of dotted around, right? In this case, we have something like this, where our set of possible edges has grown quite a bit. Okay, it looks something like this. Now, in this scenario, we have 1, 2, 3, 4, 5 cities. So 5 cities means that n-1 is 4. So we need 4 edges. So we repeat this process, picking the smallest edges and adding it together. So we know this edge is included. So actually, I think I have a red marker, so we can make it a little more clear. So we have this edge. That'll be the first one. The next smallest edge, let's call it over here. Okay. But now, the next smallest edge probably looks like either this one or this one. Actually, no. I think it's here. So that's our next smallest edge. Next smallest one after that, probably over here, and boom, we've picked 4 edges. But notice, we never went to this last city. So, we can say we know for a fact the most optimal solution has to be worse than this. Because this is the absolute minimum distance, right? It's all the smallest edges added up with 4 edges, because we know that's the minimum. So basically, if you remember our graph from before, where we said, here's the optimal solution. Actually, we'll draw it a bit higher, you'll see. So that's the true optimal solution, that we have no clue where it is. What we basically did was say, here is what it has to be at least greater than. So we may not know how much greater the optimal solution is, but we know a bare minimum for it. So in this case, it's the sum of these 4 edges. It has to be greater than that. And every additional rule we made so far helps move this lower bound up. So for example, picking n-1 edges means we went from having just the shortest edge to now having the 4 shortest edges. So now we know, all right, we're a little bit closer to getting that actual upper bound. Another thing you can do is go and pick pairs of points and just say, what is the absolute smallest pair of points? Because you know you have to visit every single city. So you can look at every single line coming out of each city and say, what is just the shortest one there? Forget trying to make a path. So we would have this line again. We would look at this and we'd say, all right, this was already removed from the set of total possible edges. So we're going to ignore that one. What's the next shortest one? Maybe this one here. We look at this guy. He'll pick the next shortest one. And we sort of repeat that until we get to this guy. And we say, okay, well, we know that this one has to be visited at some point. So we pick its shortest edge. And maybe when we're picking this one, we say we know we can't go to a city we've already been to before. So this one is sort of off the table per se. And so is this one because we already picked it for our route. So then we know that it has to be at least greater than this. Right? So we sort of move that lower bound even closer. So now we know all of this, it is impossible to get in this lower area here. We know our lower bound is here. The optimal solution is a little bit above it. And so we have a way to measure the distance between where our current solution is and roughly where the optimal solution is by using that lower bound. Now, of course, when you get to bigger and bigger number of cities, it gets more complicated. And in this really simple example I drew up here, this is actually a valid route, but sometimes it may not be a valid route. Where, maybe you have something like so, where the shortest path for this guy goes up here, the shortest path for this guy goes over here. And so maybe it ends up something like that, where it's disconnected or not a valid route somehow, some way. But again, we know that these are all of the shortest possible edges in this graph, and every city has been visited. So even though it's not a valid route, we have a minimum. We have a lower bound where we know our solution can never be smaller than that. So yeah, that is how you calculate a sort of reference for your NP hard problems. There are different techniques to doing it, and of course, you do it differently for every single kind. So this was the Traveling Salesman Problem, which is a absolute classic. If you do a computer science degree, I'm sure you'll run into it. And so it's a very interesting concept. I hope you found it useful, and I hope you guys have a good day.